wanted to introduce Chandra Krintz, who's obviously your session moderator, but she's also one of the speakers. And I want to tell you a little bit about Chandra before she gets going on her talk. Chandra is sort of an IoT systems expert and has built a lot of really interesting IoT systems. And she was named an IoT pioneer. She's won a number of awards. She was a keynoter a few years ago for the IoT conference. She and her graduate student Navina recently won a major Best Paper award. She's going to talk a little, probably that will be within the work she's going to talk about today. You have a real treat in store. She's going to tell you about the SmartFarm efforts at UCSB. And with that, Chandra, I'll let you take it away. So.
Great. Thank you, Mark. Appreciate that. So yes, I'm a computer scientist, and I'm a professor in computer science at UC Santa Barbara. And the SmartFarm Project, which I want to tell you a little bit about today, is a project that Professor Rich Wolski and I started back in 2014. And it actually started with Olivier. He participated in a capstone class project effort that I was putting together that brought in industry partners to work with students. And he brought a lot of the ideas that got us, moved us from the cloud computing area to bringing technology to agriculture, which was extremely underserved and still is today, in my opinion. So I appreciate that, and I've been working closely with Olivier throughout since. Is an effort that's funded by NSF under a sustainability call that's called CyberSeas. And this was all joint work with agriculture specialists and researchers at Cal Poly San Luis Obispo and Fresno State. The ideas that motivated us, or that this project is really targeting, is to try to identify technologies in other parts of industry and society that might be useful or might provide the building blocks that can be used to solve some major problems in ag, to make automation possible, to do actuation and control of on-farm processes. And our approach is to focus on cloud computing and data analytics, a similar background as Olivier talked about that Ag Monitor pursues, but also to consider energy use and programming systems, and try to see which of those technologies make sense to apply to systems that are on farm and that actuate and control on-farm processes and operations. So we focus on how do we bridge the gap between technologies like Google Maps and Amazon.com and Netflix, and bring those recommendation systems to fruition to provide growers and ranchers, especially smallholders, with tools that they can use to solve problems and to scale without using more land and resources. And so we look at how do we drive down the cost of sensing, how do we make these systems super easy to use, because farmers are focused on farming. They don't have a lot of extra time to learn new technologies, so they have to be super easy to integrate and use. How do we preserve privacy? And then how do we integrate with a lot of the technologies that are already in use on farms, in particular sensors and data that they collect? Our key innovation is to do something that different, to be disruptive. Most companies, or a lot of companies today, will provide sensors on farm for farmers to gather information, and then they use typically cellular connections to broadcast, to bring up that data to a cloud system. And so as farmers get more and more sensors, this becomes pretty costly. And also, pushing all that data to the cloud takes time and energy and money and bandwidth that kind of make us consider, well, perhaps we can do this differently. Agriculture is different than Netflix and Amazon.com and electronic commerce. It is vast areas that we have to be able to extract information about so that we can provide the farmers with the tools that they need. There's already lots of sensors out there, as I mentioned, and some farms aren't fully connected in these large areas, and some don't have internet connectivity at all. So we have to be able to reach these growers and ranchers that may not have the state-of-the-art equipment, but we have to be able to help them with technology if we can. Another key issue is that when you have a sensor and you're a bunch of sensors on farm or in your farm implements, and you move that all to the cloud, your data becomes shared with the vendor that you're sharing it with, the vendor who has provided you with that sensor. And this data is an economic advantage. And so this sharing that farmers and ranchers need to have control, or at least some say in who they share their data with, and how that data is shared beyond the farm. The other thing that's unique about agriculture, rather than all the other things that we use the cloud for, is that decisions are local. How much water a farmer here in Santa Barbara, a strawberry farmer, is putting on his strawberries has really no impact to a cranberry grower in the Northeast. And so what we want to do is be able to give the farmers tools to make local decisions, and then share data only as far as necessary to solve problems. So if there's, say, a pest or a disease that's moving across a county, maybe you want to share data at the county level, but you don't necessarily need to share it across states. So you want to have a real kind of intelligent system for data sharing, and that's part of our approach. Our approach takes the cloud and all the building blocks from the recommendation systems that are popular for internet computing and e-commerce, and shrinks them down into a usable system that can actually run on farm. So instead of moving all that data to the cloud, what we do instead is we take the cloud, which is code, and that's a lot smaller than the data we're collecting with all these sensors, and we move the code, which is tiny, to the farm. In order to do this, though, we have to run computer systems on farm so that farmers can do all of the data analytics or the fusion, bring all their sensors together, get intelligent, actionable insights from their data. That all has to be local. And so we study at UCSB how to do this efficiently. These computer systems have to be an appliance. You've heard of self-driving cars. This is a self-driving computer. If we can do cars, we can do computers. And so this computer is self-managing. It runs for years without any operators. You don't need an IT staff. This is really important for agriculture. But it also feels, and the way you use it is the same as you use an app on your phone or you interact with Google Maps. It has to be that simple. And so we look at how do we build systems like that to make it look and feel just like you're using an application that's online that you're comfortable with. We also then consider the machine learning and the artificial intelligence that goes into the recommendation systems that are happening in e-commerce to see which ones are going to make sense to provide recommendations for agriculture operations. We put all of this into this small computer system called an edge cloud, which runs on farm, that the sensors interact with locally. And what's nice about this is the data goes only as far as the farmer says they want that data to go. So instead of just automatically moving the data, the farmer is in control of that sharing. They can share if they want. They don't have to share. They can share anonymously. And so this gives us a lot more control, or gives farmers a lot more control over the decisions and the operations that they have. And that's important for their economic advantage. I wanted to share with you a couple of the sort of the end solutions that we target with the SmartFarm system. One is really similar or fits right in and is similar to what Olivia was saying. It's called it's an analytic system for zone identification. When you have a field, there is a lot of variation. Barus Parami asked a question in the Q&A earlier. There's a lot of variance in the data that we're collecting on the farm in general. These are, vast physical systems, complex systems. How do we manage this? And Olivia showed us how you could use images taken from as satellite data or from drones to identify areas on the farm that have similar characteristics. We did something similar with SmartFarm in that there's a really inexpensive way to gather soil properties or data that is correlated with soil properties called electrical conductivity. This is a device that you pull behind a tractor, so you can repeatedly take measurements, and those measurements are correlated with soil properties and soil health. And so what this does is gives you a really inexpensive, fast way to continuously, over the course of a season or of a year, multiple times collect data that then our system processes and identifies regions of similarity. Now, Stuart Wolf said earlier that you don't want to do precision application at a tree level, but we are no longer just applying one vast application of an input across an entire field. We can do site-specific management that finds the middle ground of this decision making. You can find areas that can be treated similarly so that you only apply the inputs, the water, the pesticide, the fertilizer, in the way that soil or that area requires. And then you can have very small areas or very large areas, depending on how efficient it is to apply those inputs. Another system or end solution that we have been pursuing has to do with frost protection. When there's going to be frost, say for the citrus industry or the strawberry industry, there's lots of ways of trying to protect against frost. There's a hard freeze, which can destroy a crop and do lots of damage, and it's extremely costly. So the one main way of trying to prevent or protect against frost is to move the air during a hard freeze, to keep some warmth in the air so that the plants or the fruit don't freeze. And they use very large fans for this to move the air. You can also use irrigation. And but both of these solutions are extremely costly. I've spoken with some farmers where the application of water for a one-night frost event, for a significant frost event, costs and uses as much water as an entire season of growth. From the fans' perspective, these are huge polluters. They have huge engines that are driving these fans. And so it costs money for gas. It puts a lot of pollutants into the air. You really don't want to use them until you really have to. But it's really hard to predict when frost is going to occur and to what duration it's going to hold. And so you need to understand sort of the topography and sort of the physical characteristics of the farm. And so we've worked on putting together, devising a sensor system that allows us to really identify fine grain microclimates. We call them nanoclimates because they're really small. The water features on a farm, or the hills, or the plants themselves play a role in these tiny little microclimates. And so what we're able to do is use a combination of a small number of high resolution, very expensive sensors, very small number, with lots and lots of really low cost, low resolution sensors, and then use software that bridges the two so that we can very accurately identify nanoclimates at a very low cost with the sensor system because of software. And so SmartFarm allows us to really bring down the cost of identifying these nanoclimates so that we can more accurately dial in when to put on water, what duration, and where on the farm to put on water, or to have to actuate and control these fans. And maybe we can even, in the future, we're thinking, working with fan companies, which we've started, to make smaller versions of these so that they are more energy efficient and we can still prevent frost in an economical way. The last one, which I'm really excited about, is something that we're focused on now. So this is, ongoing work that we're actively engaged in. And this is more far-reaching vision, where we believe that in the future, for various reasons, that we will be working with controlled agriculture environments. This is where there's some form of structure that is used to protect plants from various things, from the environment, the wind and the sun, from cross-pollination, from pests. The one that we focused on, you might have heard of urban farming or rooftop farming, vertical farming. These are, very kind of next generation ideas that allow us to experiment with what agriculture processes and automation may look like. But we look at something that's more near term. We look at citrus under protective screens. These are screening systems that are semi-permeable. We call them cups for short. Our team has access to the first production size, 4 acres, experimental cups in California at Lynn Cove Research and Extension Center. And we are studying cups with new growth, new trees for citrus to try to exclude this psyllid, this pest, ACP, that brings this citrus greening disease, which is a bacteria that's called HLB. And this is a deadly disease. It's devastated the citrus industry. It's coming to the Central Valley of California, and lots of people are studying it. One way to protect the trees against ACP, the insect vector of HLB, to produce HLB-free citrus are these screening systems, which keep out, the mesh is small enough that it keeps out the insect. So if you have this, which is necessarily an added cost to the farm, we asked the question in our research, what are the ways we can leverage these structures to do things that are much more energy efficient, that are much more automated, because we have the structure to work on. So we have heavily instrumented this cup system at Lynn Cove. We are studying how to combine sensing with physical modeling, with machine learning, to predict where the different microclimates or the nanoclimates are going to be under cups, how they're going to be different than the outside. So therefore, what operations need to be changed in order to produce very, very productive, very high quality fruit. We are also studying, if you have a structure like this, these models are going to help us understand how pesticides behave when they're sprayed under these structures, how they move through the air, how they move through the trees, so that we can help specialize and automate pesticide application. So it's extremely precise to reduce the cost of applying pesticides, but also then do it very effectively. So we eliminate the pests that are allowed in to these cup systems. We also are working with Steve Dunbars to understand how we might capture insects that are still under cups or outside of cups trying to get in, using interesting lighting and smart traps. We are also have research that looks at how do we detect breaches. As soon as there's a hole, we have to find ways of making sure we exclude the pests that are being kept out. And breaches can happen all the time. You bump into you drive a tractor into the screen. These things are going to happen in real life, and we have to automate the process of detecting, alerting, and fixing, responding to such actions. And I think one other thing that's kind of exciting is when you have a physical structure and it's actually moving and allowing some wind through, that movement can be leveraged to harvest electricity for the automation and the robotics that are happening inside. So we are looking at all kinds of different platforms for the next generation of controlled agriculture environments here at UCSB. All of our technologies and research are real. We put them in test beds. One thing that Olivier taught me is that you have to show that it works in real life and demonstrate it to farmers if they're going to use anything that we develop here at UCSB. And so we have taken that to heart, and all of our students work out in the field, literally. This is their cubicle. And lastly, I just want to emphasize that we're doing things differently here at IEE and at UCSB. Computer science and computer engineering research in here is unique because it is problem-driven and empirical. It is multidisciplinary. We work with the community and with farmers and growers in order to enable our advances. And of course, I can't do any of this without an amazing team of supporters and researchers and students. And I thank them all, and especially the Institute for Energy Efficiency. And I thank you all for listening. I'll take any questions if you have them.
Wow, that was great. So if you have questions out there, you're welcome to use the Q&A tool. If you're on the panel, if you're also a fellow speaker, you can feel free to just pipe in with your question. Stuart, if you have any questions, feel free to unmute and ask them. Okay, there's a question that's come up online. Baruz Parami has asked, is growing under screens unique to citrus, or is the method used for other crops as well?
Yeah, it's used for a wide variety of crops, and it has for decades, actually. So we have a lot of experience. The type of mesh differs. So what you can exclude and what you can't exclude, how much of the outside environment can push through changes, and all of that is really important to understand on a case-by-case basis. But yeah, we have a lot of agricultural research that we can build upon and leverage and then impact when we bring our research to fruition.
Okay, great. Others among our speakers, other speakers and panelists? Let's see. Okay, so Olivia has asked if you could talk about the cost and energy intensity of collecting data.
Yes, so it's really an evolving, the answer to that is that it's constantly evolving. We have to, sensors have come down in price significantly. The quality of sensors and the robustness of sensors have come down in price. There's an environmental issue, of course, with having a large number of sensors on farm in terms of the battery technologies. So I'd say, even 5 years ago, the return on investment from using sensors was smaller because of the cost. But since there's been a lot of interest in bringing technology to agriculture, which I'm really thrilled to see in industry and in research, that's starting to come down. And the data that we're able to collect, as I think you showed, Olivier, there's so many ways in which we can use machine learning and statistical techniques to drive decision support and to extract actionable insights for growers. And as we can demonstrate that, then that's going to happen more and more, and farmers can benefit from that. I think it's early days, so that's why it's really important that we have multidisciplinary researchers trying different things now, so that we can see, as you showed, what things work and what things don't, and where the benefits are going to be, where's the biggest bang for the buck.
I see that John has a question or two. You can see it in the...
Okay, so that was a return on investment question. Yeah, thanks, John. So the next question he has is, what sensor is needed most? Well, weather pretty much guides a lot of what growers do and the decisions they make and how the plants respond in terms of production. I think if you forced me to have, one sensor system, it would be a weather station. Soil is really important. Understanding the temperature and the moisture holding capacity of, I'd say, is really high to understand how water is used. And I think if it's not a sensor, but if it's sort of the holy grail of agriculture, I think from an analytics perspective, is yield prediction. How are my yields what are my yields going to be? Olivia hinted at when those yields are going to be optimal for harvest. If we can make those predictions, that would be fantastic for growers, but that takes lots of information and lots of data from the outside. So I would say at the extreme, that's what I'd want to get to, but that's going to take lots of sensors to do so.
Okay.
Thanks.
So, all right. Thanks, Chandra. Any other questions from,
I just have an observation. Chandra, I love the fact that you were talking about the data and how you were collecting it and it's going to the cloud and everything. But as a grower, I always wonder, like, who is collecting my data and how
Did Can the rest of
Stuart,
you?
you froze there a second. I heard the part about who's collecting my data. Are you back?
I don't think so.
Okay, so what we could do is we could maybe take this up in our panel discussion when we get to it later this afternoon, later this morning.
Absolutely, but it's one example of limited broadband access in rural areas. I
Yes.
kid you not, it happens to me 3 or 4 times a day.
Yes.
But 5G should really change that, right? I mean, isn't 5G going to make that a lot better?
If it
It'll
was
come to
deployed by the public goods,
cities.
yeah, but if it's a private enterprise, you know, they may put only antennas where there's a return. And so if you don't have a hospital or a school in the middle to drive the adoption, you know, there are a lot of dark spots. There's actually a CPUC app. It's a mobile app you can download, and you can report a spot where you don't have broadband in California, and the CPUC will collect that data and try, you know, in the next cycle to make sure, you know, the utilities or the carriers are incentivized. So it's not the old Bell Lab system, John, where, you know, there's a dial tone everywhere in the U.S. It's a little bit more driven by revenue.
But I'm wondering if, you know, the whole millimeter wave, really high capacity changes your calculation, Chandra, in terms of the need for an edge cloud rather than a central cloud. Certainly, historically, absolutely, I understand the need for it, but
Yeah, no, I think you have a good point. If the turnaround is low latency, sufficiently low latency, then that would make sense. Turns out, though, the computation of software, the analytics, still takes time. And so, yeah, whether you do that on farm or remotely, it can be both. It can be some combination to drive local decision making. So, yeah, I'm very excited about 5G and to see what's going to happen, and hopefully these edge systems will bridge us to that period of time when those technologies, like Olivier said, come online and are available.
The other thing, Chandra, is your architecture enables a hybrid model. There are radio frequency networks that are very
Oops.
we're losing people.
Wow.
Hello, can you hear me?
Yeah, there you go.
Now we can.
I'm in San Mateo, so I don't have any excuse. I was saying that there are radio frequency bands that are free. And so
Yeah.
with your architecture, what you can do that the cloud cannot is you could have a bigger pipe a few times a day where you're transmitting codes and results, but you can use a 1 mile, 10-mile radius to collect data and have your small cloud at the farm to do all the computation. So you know, I think that the 5G could be used as a larger pipe to 1 or 2 locations at a large farm like Stewart's. And then there is something else, you know, more like radio frequency based, like in Europe, to track cows in the Alps, which is how, you know, Laura literally started in Grenoble. And you know,
Awesome.
and you know, it's free, but if the cloud is 10,000 miles away, or, you know, 1,000 miles away, then you need, you know, 5G, you know, every acre, and that's where the equation is difficult.
All right. So maybe perhaps we could take this up in the panel session if we want to pick this thread up, because this is really good. Stuart, welcome back. Sorry we lost you. But I think we're going to pick up your point in the panel session though. So with that, I'll head back over to you and introduce the next speaker. And thank you so much. That was really great. Thank you.
Thank you very much.